Right? What we're going to do in this lab is convert gravitational potential energy into kinetic energy. Okay, we've been looking at examples of that all the way along here. That's what you worked on yesterday with Mr. Baldwin. Okay, when I wasn't here, you worked on conservation of energy, EI equals EF, conversion of energy from one form to another, work energy theorem, all that kind of comes together in this lab. It's a very simple lab. We're going to build a ramp, and we're going to run a cart down it. Okay, we like to keep things simple. Okay, the things that we need to measure out of this lab, the initial height of the ramp. Okay, why are we going to need the initial height of the ramp? It's going to allow us to calculate our potential energy, okay, our starting or initial energy for the lab. Okay, other things we're going to need to measure: the distance of the ramp and the time it takes the cart to travel down it. Right? That's going to allow us to calculate the acceleration of the cart using a formula you'll never use again. Okay, at least in Science 10. You'll use it again in Physics 20. Okay, but we're going to use it here in Science 10 today just in order to get the acceleration that's happening for this cart so that we can calculate its final velocity at the bottom of the ramp. Okay, we can't use v equals d over t because its velocity is changing as it goes down the ramp. Okay, so what we want to do then is know the velocity at the bottom of the ramp, and then we can figure out how much of the energy we had at the top was still there at the bottom. Right? Theoretically, they should be exactly the same number. Reality is a little different. Okay, we're going to lose some energy as this cart goes down the ramp. Okay, even though these ramps are, incredibly skillfully built by Mr. Dickey and myself. Okay, they are still, of course, not perfect. Okay, and neither are the carts that we're going to run down them. Okay, the carts we're going to run down them look like this. Okay? All right? They are specifically designed for those ramps. Okay? We did a lot of measuring. Okay? Measuring is important. Now, these are pretty good carts. Like the wheels on them are, pretty low friction. Right? There's still, but I can still hear it. Okay? If I can hear the sound of that thing spinning, I know it's losing some energy due to friction. Okay? And obviously, if it kept spinning, it would probably get warm and wear out the bearings and things like that. Okay? There's definitely still some friction there. And of course, as it goes down in these grooves, okay? I mean, it's going to hit the sides of the grooves a little bit as it goes down. There's going to be places where energy is lost. What we want to see is how efficient does gravitational potential energy, or how efficiently, sorry, does gravitational potential energy convert into kinetic? Okay? That'll be kind of the purpose of the lab. All right. And I don't have the problem with the design or anything there. It was not good. Sorry. Okay, so the problem we're investigating here is how much of the available potential energy is converted into kinetic energy in a mechanical energy conversion. All right, now our manipulated, responding, and controlled variables here. Looking at this experiment doesn't start unless I do what? Right, okay, I do work and I give this thing some initial potential energy. That is the start of this lab. That is the energy that I'm going to give it in this lab. Okay, therefore it is the manipulated variable. Okay, I'm the one that gets it going. Okay, the initial potential energy is a result of what I'm doing. I'm manipulating this system. If I don't put that cart at the top of the ramp, nothing will happen. Okay, so the manipulated variable here is going to be the initial potential energy. Now, if we look back at the problem, okay, oh, right, can't use that here. Okay, if I look back at the problem, okay, how much of my available potential energy is converted into kinetic energy? Okay, that should give you an idea of what one of the other variables might be here. Right? Now, other variables. When we're running this lab, okay, are we going to change the height of the ramp? We're going to make the ramp once, and that's it. Okay, we're going to make sure it stays the same throughout the lab. We don't want to, as the cart is traveling down the ramp, grab the ramp, make it steeper. Okay, that's hardly going to be a fair assessment of what we're doing. Okay, also, we're probably going to use, the same cart through every trial. Okay, basically anything that could affect, the outcome of our lab. Okay, that needs to be kept the same each and every time. Okay, for our hypothesis, we need an if and then statement. The if part of our hypothesis should probably talk about the law of conservation of energy. And what that says about energy going from one form to another. Okay? Law of conservation of energy says something about that. So if the law of conservation of energy says this, and describe the experiment, okay, then what are you going to see in terms of the relationship between the kinetic energy at the end and the potential energy at the beginning? Okay, according to what this says. Okay, so our hypothesis is kind of the perfect physical world idea. Is it going to be right or wrong then? It's probably going to be wrong. We're talking about, in our hypothesis, the perfect physical world, and we're running an experiment in the real world. Okay, so it's probably not going to end up being true. Is that okay? Yes, it is. Okay, what we're trying to find out is it really 100% efficient? Probably not. Okay, that's okay. We'll find that out, and then we'll say in the conclusion what it really ended up being. All right, so as I said before, things that we're going to need to record. In order to calculate the potential energy, we need to know the mass of the cart. Okay, we need to know, and the cart's mass is right here, because I already measured them. Okay, 0.470 kilograms is the mass of the cart. Okay, the initial height of the ramp. Well, everybody's ramp is probably going to be a little different. Okay, so you'll have to measure it with the meter stick over there. Okay, measure it to, let's say, when you put the car on it, put the car so that the back wheels are right here at the very top edge of the ramp. But then measure, okay, to essentially where the car sits. Okay, let's say measure to the top of the ramp. That's probably the easiest thing. Okay, so just measure right to the top of the ramp from ground level. Everybody okay with that? Okay. For the kinetic energy, mass of the cart. We already know that, and it's not changing. Okay, the cart's not going to change mass as it rolls down the ramp. Okay, the distance traveled by the cart after it leaves the ramp. Okay, here's the strange thing that we're doing here. Okay, we're actually going to have to start the timer once the cart is on the floor. This is what's going to help us to calculate our kinetic energy. Okay, what's going to happen is after the cart leaves the ramp, it's going to roll, but it's going to slow down and eventually stop. Everybody with me there? Okay, if I time how long it takes it to stop and how far it goes while stopping, I'll be able to calculate the force of friction acting on the cart. It'll be the only force acting on the cart once it's on the floor. Okay? From there, I can calculate the work that was done against friction in slowing the cart down. And that number will equal the kinetic energy it had at the bottom of the ramp. Okay? Because friction is going to eat up all the energy it had at the bottom of the ramp. Everyone follow? Okay? So, sorry, Haley, question? Well, as best you can, yeah. There's going to be a little bit of reaction time error there. Yeah. Okay, so what we'll really have, okay, so here's our ramp, and we'll start the cart once the cart, or start the timer, sorry, once the cart is right here on the floor, both sides. I mean, once it hits kind of started, your reaction time will basically make sure that back wheel's on the ground. Okay, it's going to slow down, slow down, slow down, and eventually come to a stop. If I know how far it goes, okay, and how long that takes, I'll be able to calculate the acceleration of the cart, multiply that by the mass, and that'll give me the force of friction. Okay, and we already said we're going to calculate the acceleration. There's a formula in here which I'll go over in a minute. Okay, that'll give me the force of friction. If I multiply that by the distance it traveled, force times distance is work. Okay? Whatever work is done against friction is what takes away the kinetic energy it had at the bottom of the ramp. So that's how I'm kind of indirectly going to calculate the kinetic energy at the bottom of the ramp, because there's really no way for me to know how fast it was going at the bottom of the ramp. Okay? I don't have a radar gun. Okay? I don't have anything like that where I can calculate how fast it was going, okay, or measure how fast it was going. This is the best way to do it. Everyone follow there. Okay? So we're going to measure how far the cart travels and time how long it takes to stop. We'll do a few trials of that just to make sure we get a good average. Okay? Then we'll compare the force times distance here with the amount of energy it had up there. Okay? And then we'll know how efficiently the energy was converted as it traveled down the ramp. All right? Questions on that part of it? Okay, now, to calculate the acceleration, okay, that's in here, right here in part 2A, and it says that in the analysis here as well. Okay, we're going to calculate the acceleration of the cart by multiplying the distance by 2 and dividing by time squared. Okay, that'll give us the acceleration. You're never going to use that formula except for this lab in Science 10. Okay, once we have the acceleration, we'll multiply it by mass. That's what it says here in part 2B. Okay, multiply mass times acceleration times distance, and you've got your work done against friction, and thus your kinetic energy at the bottom of the ramp. Okay, then it's just a matter of comparing the two. All right, so your analysis is, a lot of it is the calculations. Okay, the first 3 of the 5 questions are just showing your calculations, okay, for the stuff that it said to do in the procedure. So it says calculate the work done in putting the car at the top of the ramp, show your work. Okay, how did we say we were going to do that? What kind of energy does it have at the top of the ramp? Potential. How do we calculate that? M times G times H. Okay, so that's an easy one. Okay, all we got to do is go M times G times H. We know what M is, we know what G is, and we're going to measure H. Okay, for part 2, calculate the acceleration of the cart using your average distance and time. Okay, and it says that C, initiating and planning, step 2A, so we'll go back to that. Calculate the kinetic energy of the cart, okay, using what it says to do in step 2B, which I already went over. Okay, show your work on that. And then for 4 and 5, basically for number 4, just tell me what I just said in the podcast here. Okay, how did you determine the potential energy? Okay, well, it has something to do with this. Okay, how did you determine the kinetic energy? That's that whole thing I talked about with friction there. Okay, and then for number 5, that's on you. How do they compare? Okay, how do they compare? Is it a lot less, a little bit less? Is it pretty efficient, not very efficient? Okay, things like that. We're going to talk about percent efficiency on Friday. All right, so you'll be able to calculate after Friday the efficiency of that conversion. It's pretty easy. It's your final energy divided by your initial energy multiplied by 100, just how you would calculate the percentage of anything. Okay, and then you give me reasons for why it's, you know, very efficient. Where were some places where energy was lost? Things like that. That's your big question. That's the one that shows how much you understand what was going on. Okay. And then conclusion and evaluation, same as always. Again, we said that our conclusion may have to say that our hypothesis is not correct because it was a perfect physical world hypothesis. Okay, and we did this experiment in the real world, and that's okay. Okay, just in the conclusion, talk about some of the same things you talk about in analysis number 5. All right, so charts that I have, I think these charts are in your template, right? Okay, so the distance in meters, okay, that's going to be how far it travels, measured from the bottom of the ramp. Okay, your time, how long does it roll for? Okay, acceleration, that's what you're going to calculate using this formula here. Okay, so 2 times d divided by t squared, right, and plug that in here. Your initial potential energy, it's going to be the same number every time, right? This number is the same every single time because we're putting it on the top of the ramp, right? We're going to do 4 trials just so that we get a good average. No, don't copy these. These are from another time. Okay, you're going to get your own data. These are just samples. So 0.470 times 9.81 times 0.25 meters, just secondly. Okay, and then kinetic energy, that's going to be different each time. Okay, so do your calculation, m times a times d for each trial. Okay. All right, so you're going to do that for each trial. Okay, then listen in here, guys. Okay. when we get to this last part here about calculating the kinetic energy, sorry, I think I said do it for each one, but I didn't mean that. Okay, here's what I want you to do. Okay, you're going to calculate your accelerations for each one, and then down here, I want the average. Okay, we're going to calculate the average acceleration down here. All right, so add these together and divide by 4. Okay, that's going to be the acceleration you're going to use. You're only going to do this calculation here once as well. Okay, you're going to do this one right here. M times A times D, using the average acceleration. All right, so then we can compare this number, which we know is the same for every trial, with the average kinetic energy that we calculated for the entire lab. Okay, that'll tell us, those will be our comparison numbers. Okay, everybody good with that? All right, so the things we have to do then, we have to build the apparatus, so you got to stack up maybe a couple of binders, okay? Probably not more than 2 binders. It doesn't need to be really steep. In fact, if it's really steep, the cart will travel too far, all right? What I found when I set this up was 25 centimeters is about as high as you want to make it. Otherwise, it's just going to hit the wall before it stops, okay? We want it to be able to slow down and stop in the space we have, okay? Everybody follow there. All right, so what we might want to do is have like one group working along the back, one group working along the front, and then a couple of groups in the rows, okay? It tends to go pretty straight. These ones don't turn very much. Well, I've got, what have I got there? 8 ramps, so maybe groups of 3 or 4, okay? No, because there's drama classes going on in there, okay? There should be enough room for us to do it in here, okay? All right, so we're going to need one person to be a timer in each group, okay? One person to be a timer, one person to measure. My suggestion on the measuring would be measure all of them at once, okay? So take a board marker, okay, and just mark on the floor with the board marker, like put a line where the cart gets to, okay? Put a 1 for trial 1, 2 for trial 2, okay, and then measure them all at once, okay? What's that? Yeah, it erases. You can just rub it right off with your foot. Okay. If it doesn't come off with your foot, spray a little bit of that on the floor and rub it with a paper towel. It comes right off. Okay. Questions on how that's going to work? Okay. Well, let's get to it. Okay. I want to do a quick clarification here of the calculations that you need to do to fill this chart in. Okay. We're going to simplify here a little bit, just so that we don't have quite so much stuff to do, okay? What I want you to do is average your distances, okay? So take them, add them together, divide by 4. Average your times. Take them, add them together, divide by 4. Calculate the acceleration once, okay? That'll be the average acceleration over the whole lab. That saves us doing 4 acceleration calculations, okay? We'll just do 1 with the average distance and average time, okay? So we'll have our average distance, our average time, okay? We'll calculate our average acceleration, okay? And that'll be, remember, acceleration is going to be 2 times the average distance, okay, divided by the average time squared, okay? Do that calculation once, that goes here. That number gets used to calculate your average kinetic energy by going mass times acceleration times distance.
So do we leave the other blocks for acceleration?
Yeah, just leave these blank, okay? It's just when I built the grid, there was no way to not have them there. Yeah. If you already did it the other way, that's fine. Yeah. Okay. This way just involves a little less work. Yeah. Yeah. Well, it's kind of the same thing because it's a straight line. Distance and displacement. Well, not really. We're going to imagine it didn't. Yeah.